Not many people here today. I guess it's Friday. Let's see. I'm going to keep talking about regression today. We'll be doing regression all of next week as well. And we'll continue doing regression when we get to correlated data. And we'll continue doing regression when we get to survival data. So lots of regression. Everything is regression. We started last time representing regression models in matrix form, which is convenient because if we can write our model in this form, a vector of responses y equals a, quote, design matrix X times the vector of coefficients beta plus the vector of residuals. Once we can write the model that way, then the slides that are coming show us how to estimate the model, how to get estimates for the coefficients beta, how to get standard errors for them, and then how to do inference on the betas. So let me just review what we have here. If we have this simple linear regression model, then to fully write out the model for our data, we would want to say y1 equals beta 0 plus beta 1 x1 plus epsilon 1, and y2 equals beta 0 plus beta 1 x2 plus epsilon 2, dot, dot, dot. There's n expressions of this model for our n observations. We can represent all n of those in one expression using the vector and matrix style representation. The way we can do that in this case is with a design matrix that looks like this. Capital X, it has ones in the first column and it has the x's in the second column. So whenever we do x times beta, we are recapturing this. This x times beta, n by 2, beta is 2 by 1. So when we multiply them together, we will have n by 1. We're going to have a vector, one expression for every individual. And the ith element of that will be the ith row of x dot producted with beta, the vector. For example, the first entry of x beta will be 1 times beta 0 plus x1 times beta 1. And then the second element will be 1 times beta 0 plus x2 times beta 1, and so on. Here's what it looks like when we add one more predictor or covariate variable to the model. Now there's two of them, x and z, and the design matrix just adds one column for the z's. Now the first element of x beta will be 1 times beta 0 plus x1 times beta 1 plus z1 times beta 2. Okay, I think this one's new. In the context of that hypothetical example that we've seen of what was your major in college and what was your salary, or what was your major and what was your gender, and then what was your annual salary. And suppose that we have 20 individuals. We have 5 males who majored in science, 5 females who majored in science, 5 male arts, 5 female arts. And suppose we organize them this way. The first 5 numbers in our data set, the first 5 rows, are the science males. Next 5 rows are the science females, and so on. Then we can represent an Anova model. Anova makes sense here because we have only categorical predictors. So we're not estimating slopes so much as just comparing means. So you might think in terms of Anova, but we've seen we can equivalently represent an Anova model as a regression model. And it's a little more involved to figure out what capital X is here, but let's talk about it. Capital X is written this way in this case. This is 20 by 3. Every element in here in this matrix, like that first one, is a 5 vector. It's a vector of 5 ones on top of another vector of 5 ones, on top of another one and another one. So this first column is the usual column of ones, which picks up an intercept in our model. Every individual has the intercept. And then let's consider just this first row, which is actually composed of 5 rows, all the science males. Because it is science for these individuals, we coded the degree covariate to be 0 if you are arts and 1 if you are sciences. So for everybody who's in the sciences, which would be these guys and the next 5 rows, males and females, I want a 1 to turn on or pick up, add the degree type effect, main effect. So for the first 5 individuals, I want an intercept, I want degree for science, and we also coded males as 1, females as 0. So since these 5 rows all are science males, I want intercept, science effect, male effect. Back when I originally introduced regression representation of Anova, I said that it is standard in a problem like this, in an Anova model, to impose some kind of restriction on these terms. This model right here, if we didn't do any restrictions for identifiability purposes, would have mu and 2 D terms and 2 G terms. That's 5 parameters. And we don't have, that's an over-parameterized model. We have to reduce somehow the number of parameters in order for us to be able to fit it. A standard way to do that is to force the D's to sum to 0 and to force the G's to sum to 0. Now there is only 1 degree effect and 1 gender effect. It goes positive for males, goes negative for females. Positive for sciences, negative for arts. So science males are going to be mu plus D plus G. Science females are going to be mu plus D minus G. So that's how we're representing male versus female. You either have plus G or minus G. Then we have arts male, so 1 minus 1, 1, and arts female, 1 minus 1, minus 1. If we ran this X beta operation, we would have this represented in one object, all in representations from our model. Long story short, we can take an Anova model and write it as a regression model. Then, like if we wanted to test, is there a gender effect or a science effect, we would test the coefficients of this model. Any test about this relationship will translate to tests and inference on the coefficients in the regression model. So, let's keep going. We have now seen how to represent a variety of regression models in a compact form. Let's keep thinking about what's next. what we want to do is not just fit a model, but use it to do statistical inference. To do statistical inference, we already know we need an estimate of the parameter of interest. In regression, our parameters of interest are going to be these beta coefficients. So we need estimates of them, and we need standard deviations of them, and we need to know sampling distributions for them. Those are the components that are required for inference. So we need to figure out, how do I estimate the beta vector? What are its standard deviations? And which sampling distribution, t, normal, f, chi-square, which one should I use to get p-values and confidence intervals? Okay, one way we're going to motivate this is with likelihood argument. We've seen likelihoods. Suppose that our data, this is not regression data, this is just univariate observations of a single variable, no covariates. So if we just had a random sample from the normal distribution with mean mu and variance sigma squared, then we know what the likelihood is. A likelihood is a product of either PMF or PDF values evaluated at all of our data. This is the normal PDF. So the likelihood, roughly speaking, the, quote, probability of seeing our data, if these are the parameter values, is represented by this product of normal PDFs. In the simple linear regression case, when yi, let me write it down for real quick here. Simple linear regression case, SLR, the model is just yi equal beta 0 plus beta 1 xi plus epsilon I. Simple linear regression means just one covariate. So if our model holds, our model would say that these epsilons are independent and identically distributed from a normal distribution with mean 0 and variance sigma squared. That means that the distribution of y given x is itself normal, and it has a mean beta 0 plus beta 1 x, and a variance equal to the residual variance. That can be visualized if you think back to the original picture we made to motivate regression. We have data, and we say for any particular choice of x, call it x0. Well, so let's step back a moment. We have this data, and we think that underlying the data is a line. On average, y is linearly related to x. But that's on average. We still see this bobbing around this deterministic relationship. At any particular value x0, we have that the response is normally distributed about the line. That blue curve is just the residual curve, normal with mean 0, variance sigma squared, rotated and put on the line at that specific point. If this is what I know about my data distributionally, then we can compute a likelihood. The likelihood of the beta coefficients, beta 0, beta 1, and also sigma squared is an unknown quantity. The likelihood would just be the product, I equal 1 to n, of the normal PDF. So we have 1 over the square root of 2 pi times sigma as a constant out front, and then e to the minus 1 over 2 sigma squared. And now I want to do observed value of y minus its mean. And according to our model, the mean of y is that. So this is just normal PDF using this as the parameters, or that to get the parameters. That's where this came from. Product of a normal PDF with mean beta 0 plus beta 1x and variance sigma squared. What follows is just a little bit of algebra and differentiation to show you how we can go about getting estimates. If we write down a likelihood, that means what you're going to do is maximum likelihood based inference. And maximum likelihood is the technique of writing this down and then searching around the parameter space for the choices that make it biggest. If a likelihood is, roughly speaking, the probability of our data for given choices of the parameters, then a sensible approach for estimating the parameters is to find the values that make it most likely to have seen your data. If we wanted to do that, how do you optimize a function in terms of some parameters? You do calculus. You differentiate, set it equal to 0, and solve for those. You're looking for a maximum, so you want to find where the slope is 0. And assuming that that's a concave relationship, then wherever the derivative is equal to 0 is the maximum. It's often easier to do maximum likelihood calculations if you log transform the likelihood first. It's messy to do derivatives of e to the stuff, for example. And it's equivalent. Maximizing the likelihood, whatever betas do that, they will also maximize the log likelihood. So this is just what happens when you log transform. The last line there is the simplest version of it. We have a constant out front that doesn't have any of the parameters in it. We have something that has sigma squared in it. And then we have something that has the betas and sigma squared in it. So then to estimate the betas, we would differentiate that log likelihood with respect to beta 0 and differentiate with respect to beta 1. You would set both of those equal to 0 and solve the system for beta 0 and beta 1. When you do it, your introductory regression book would show you this formula. The estimated slope, the MLE, maximum likelihood estimator of the slope parameter, is sample mean of the responses minus whatever the MLE of beta 1 is times the sample mean of the predictors. And similarly, if you plug that relationship into the expression for beta 1, you can solve for beta 1 hat. In the context of simple linear regression, just a single covariate, beta 1 hat is of this form. If you look at this, what it looks like is in the top, it looks like a covariance kind of calculation. Let me just write a couple of things over here. We have y, x. I'll do it the other way around. Our data consists of pairs, x1, y1 for individual 1, x2, y2 for individual 2, up through xn, yn. The sample variance of those y's, let's call it s squared y, would be 1 over n minus 1 times the sum over all I of yi minus its mean squared. Similarly, the sample variance for the covariance would be 1 over n minus 1, sum I equal 1 to n, xi minus x bar squared. A covariance, these are estimates of variances. Suppose we have two random variables, u and v. The covariance between u and v is defined as expected value of u minus its mean times v minus its mean. So this expression, sum I equal 1 to n, yi minus y bar, xi minus x bar, if you divide it by n, or n minus 1, it would be an estimate of the covariance between y and x. If you wanted to estimate this quantity for the sample, you would replace an expected value with an average. So for example, the variance of y is equal to the expected value of y minus its mean squared. And we estimated it by replacing the mean of y with the sample mean and an expectation with basically an average. Add them all up and divide by not n, but n minus 1, just for technical reasons. But roughly speaking, s squared y is the average square deviation from around the sample mean of y. So this piece right here shows up in the expression for beta 1 hat. It's in the numerator. And what's in the denominator looks like this piece. So if you forget about the constants that go out front, dividing by n minus 1, if you took the ratio of those two terms, the covariance of y and x divided by the variance of x, that's what beta 1 hat is. A covariance, if you scale it by dividing by the two standard deviations, you get a correlation. So this numerator is proportional to the correlation between y and x. What gets divided by is roughly the variance of x. So beta 1 hat will tend to increase away from 0, get big positive or big negative when y and x are correlated with each other. If they're positively correlated, beta 1 hat will be big, positive. If they're negatively correlated, beta 1 hat will be negative. And then the magnitude of it is further affected by how variable the x's are. If the x's are all over the place, then beta 1 hat gets shrunken towards 0. Whereas if they're not, beta hat increases. So the value of beta 1 hat represents the correlation between x and y, and it also, but it's a scaled version of that. Slope of a regression line is related to a correlation between the y and the x. That was for the simple linear regression model. We just figured out manually from scratch how to estimate beta 0 and beta 1. Take the likelihood, maximize it using derivatives with respect to beta 0 and beta 1. So what about another model that has an additional covariate in it? Now I have two covariates, x and z, and let's figure out the coefficients that estimate this, the MLEs of the betas. We could go back and do the same thing we did here. differentiate with respect to beta 0, then differentiate with respect to beta 1, then differentiate with respect to beta 2, set all three of those equal to 0, and solve the system of three equations. That gets tedious if you had to do that for every single model. And this is where it becomes handy to represent our regression model using the matrix expressions. So here's why. If we say y the vector equals x design matrix times beta the vector plus epsilon the vector, then similarly to how we said that y is normal with mean equal to the line and variance equal to sigma squared, we can say that y the vector is multivariate normal with a mean vector defined by x beta. And with multivariate data, you have not only variances of each of the components, but you also have covariances between the components. If I have n observations, then I would be able to compute a variance for each observation, but I'd have to, if I was going to be general as possible, allow for correlations between individuals. The general form that you would see for an arbitrary regression model, y equals x beta plus epsilon, is that y, once we know x, is multivariate normal, n-dimensional normal, with a mean vector equal to x beta, and a variance covariance matrix that's n by n. Call it capital sigma. What we are doing in terms of regression is making some simplifying assumptions about that covariance matrix. In particular, so far, we have been assuming that the variances are constant. That would mean that every individual has the same variance. So if we're going to think about a capital sigma covariance matrix, it would equal a variance for individual 1, a variance for individual 2, individual n. And then in the off diagonals, we would have a covariance between individual 1 and individual 2, and every other paired covariance. And this is symmetric. So if that's what we're going to use, there's lots of parameters in there. There's a separate variance for every single individual, and there's all those covariances as well. If we have the simplifying assumption of constant variance and independence of our individuals, if the epsilons are IID, then there are no covariances in the off diagonals. So if we assume epsilons IID, then this simplifies to an expression that we can just say is a scalar, sigma squared, times the n by n identity matrix. All the identity matrix is 1s down the diagonal and 0s everywhere else. So that would look like sigma squared, dot, 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 sigma squared, and 0s everywhere else. All right, so bottom of the screen here, we're saying y, the vector, multivariate normal, mean x beta, and most generically, we could say a covariance matrix capital sigma. But under our assumptions so far, we get to simplify it to just a single scalar number, sigma squared, times the identity matrix. So then here is, right, that's what we're going to have. But let's think most generically right now. Let's keep that capital sigma as arbitrary. This gets handy, this kind of representation is handy when we get to correlated data. When we hit correlated data, we won't have IID residuals because we have repeated measurements on the same individual. So for now, treating capital sigma as an arbitrary covariance matrix, the likelihood is a multivariate normal PDF. So take my word for it, it looks like this. Instead of a 1 over square root of sigma in the front, we have a determinant of a covariance matrix to the minus 1/2. And instead of e to the minus 1/2 sigma squared times yi minus x beta squared, we have a quadratic form of vectors weighted by a covariance matrix. This is just the multivariate version of that normal likelihood we saw earlier. I'm not expecting you to be able to reproduce the math that follows, but just follow along as well as you can. We're mimicking what we did earlier with a univariate normal likelihood. We will again log transform. And after log transforming, we have this expression. We can carry out the calculations in this quadratic form. And when we do that, we have something in terms of beta and another term in terms of beta. So if we want to estimate beta, we could differentiate that log likelihood with respect to beta, set it equal to 0, and solve. What's handy about using the matrix representation is we can differentiate once with respect to the whole vector beta. So you may not have seen how to do that before, but for example, the derivative of this expression with respect to beta, it's like a constant times the variable you're trying to differentiate with respect to. So what you're going to get back is just the constant. And similarly over here, this is like a squared term of beta in a sense. There's beta transpose and beta. So we're going to get, when we differentiate this, something like 2 times a constant times beta. I don't go through all the calculations, but if you do them, it's not actually hard. But if you differentiate like I was just saying, then set it equal to 0. Oh, I have it right here. Okay, so this is the derivative. And setting this equal to 0, you can move this thing over to the right. And then if you pre-multiply both sides by the inverse of this, you'll isolate beta. So beta hat is this expression. The maximum likelihood estimator of a regression, a vector of regression coefficients, is this x transpose sigma inverse x inverse x transpose sigma inverse y. Under the IID assumptions, capital sigma is that little sigma squared times the identity. We have this, in which case this piece right here is 1 over little sigma squared times the inverse of the identity matrix. And the inverse of the identity matrix is the identity matrix. And if you multiply any vector by an identity matrix, you just get the vector back. So this piece right here, I have 1 over little sigma squared. This makes it just sigma squared. So I have a little sigma squared out front, and then just x transpose x inverse. Over here, again, I have 1 over little sigma squared, and then something that goes away because it's just an identity matrix. So we have a sigma squared out front. Here's a 1 over sigma squared. That means the sigma squareds cancel. And we're left with a simpler expression for beta hat. Under classical assumptions of the linear model, constant variance, normally distributed data, the maximum likelihood estimator of beta is x transpose x inverse, x transpose y. Let me show you an example. Let's go to the weight height data. These are simulated data. Okay. So these are, I don't think we've actually looked at these yet, but they're just made up data on weights and heights, and we can play with regression with them. So let's read these in. We have 240 individuals. Here's the first few rows. Height, weight, gender, race, and a totally irrelevant variable, college degree. Okay, let me find a regression model down here. Okay, here's one regression model that we could do. Let's model weight as a linear function of height. Lm is R's function for doing linear models. And the way you access it, I would say do $Lm to see the help file. But you call Lm and you say response tilde, as in model the response in terms of an intercept and the predictor variable height. So let's run this. If you do summary of the fitted object, you get coefficient estimates, standard deviations, and p-values. This is standard output from a linear model. The piece where most of the action is here. That tells us in the first column of that the estimate of beta 0 and the estimate of beta 1. Beta 0 hat is minus 159.8. Beta 1 hat is 4.9. The next column are standard deviations for those estimates. The next column is the ratio of the estimate to the standard deviation. And then we have a p-value. This right here is a t-statistic. It's the t-statistic that would apply if you wanted to test whether that beta coefficient was equal to 0. If we have this model, beta 0 plus beta 1 xi, suppose we wanted to test whether beta 1 is equal to 0. That would be asking, is there or is there not a linear relationship between x and y? In order to do that, one standard test statistic form, it's called a Wald test. Wald test looks like estimate of the parameter of interest minus what the parameter is under your null hypothesis and divided by the standard deviation of the estimate. So if my null hypothesis is that beta 1 equals 0, this just equals estimate divided by SD of estimate. And R, by default, and pretty much any statistical software by default, will give you p-values for that null hypothesis by default. We can test anything we want. We're not restricted to this particular test, but it's what R always demonstrates. It would be very common to ask, is this slope equal to 0, yes or no? And in the R output, you have it right there automatically. Okay, so that's what regression looks like in R. What else did I want to show? Oh, let's match that. Let's see what it looks like to do this y equal x beta stuff. I have that down here. Line 99, beginning. I'm going to reproduce what we just did, but I'm going to do it manually. So to do regression in that matrix representation, you need the design matrix, that capital X that's n by p. With a simple linear regression model, all we need is a column of 1s next to a column of the x's. So that's what I'm doing in this capital X definition. If you do C bind is column bind. So like if I said 1 to 5 and bind that to 6 to 10, column bind, you'll get a column for the first element next to a column for the second. If I were to do C bind 1, comma 6 to 10, it will expand the first element to match the length of the second. So when I did this, it gave me what we want, a matrix with 1s in the first column and the x's in the second. Design matrix. So then, using that, we can compute beta hat. I think it's fair to just ignore these instances of drop. Drop is a function that if you start with a matrix and ask, say, just for one row, or in particular if you start with a data frame. If you have a data frame and you ask for one row or one column, it will give it back to you in, like if you ask for a row, it'll give it back to you as a 1 by however many columns you have array, not a vector. So if you're trying to pull out individual rows or columns of a data frame, you can run into challenges if you try to use them to do matrix operations. I don't think it matters in this case, but I have the drop in there from a previous semester. So big picture here is that we're doing X transpose X inverse times X transpose Y. This is mimicking this. We have the design matrix, so I just need to do X transpose X and invert that, multiply by X transpose Y. You can invert a matrix in R using the solve function. T of X means transpose X. This means matrix multiplication. You don't want to use just asterisk. Right. So let's have a look at this. Beta hat should match LM. So the key is, if you want to do these types of calculations, the key is to get this right. And then the same formula applies no matter what your model is. It's always X transpose X inverse X transpose Y. I'll come back to that script probably Monday to show you some more. Let me finish the next couple of slides here. What I want to do next, we just figured out how to estimate the coefficients of a regression model. Maximum likelihood does it for us. Then we want to know about the sampling distribution of beta. To do inference, you need to know estimate, standard deviation, and distribution. Let's figure out the mean, the expected value, and the variance of beta hat. The variance of beta hat is going to contain these standard deviations. If beta is a vector, like it is in our case, beta 0, beta 1, just two elements for a simple linear regression model. Let's put hats on these to indicate these are the estimates. In the slide, we have that the expected value of beta hat is equal to beta. Beta hat, computed the way we're computing it, is unbiased. And when we say variance of beta hat, if we're dealing with vectors, then the, quote, variance of a vector is a covariance matrix. So it's going to be a 2 by 2 matrix with a variance for beta 0 and a variance for beta 1 and a covariance between them. This is also symmetric. If you want the standard deviation of beta 1 hat, for example, you could then come and get the second row, second element, and take the square root of it. So let's see, the expected value of beta hat. That's the expected value of the expression for beta hat, x transpose x inverse, x transpose y. Since the x's are constants, as far as we're concerned, this expected value is only with respect to y. In regression, the x's are treated like they're fixed. So those are just constants. All that x stuff is just constants, which means they can be pulled out of the expectation. And then the expected value of y, according to our model, if y equals x beta plus epsilon, and epsilon has mean 0, then the expected value of y is, what am I doing here? I want expected value of beta hat. Expected value of, expected value of y is just x beta, because the epsilons have mean 0. So in this expression, expected value of beta hat is pull the constants out and have just left expected value of y. And according to our model, the expected value of y is x beta. Now we have an x transpose x inverse next to x transpose x. Those cancel out. We have that beta hat is unbiased. And I also wanted to show what the variance covariance matrix of beta hat is. This is the variance of the expression for beta hat. And I have on the previous slide the variance of a matrix or vector of constants times some random vector equals A, the matrix or vector of constants, times the variance of the random vector times A transpose. So the variance of this mess, these are constants as far as we're concerned. I can pull them out front, have the variance of just y in the middle, and then the constants out on the side again, transposed. So this is the general expression of the variance of beta hat. When we have the simplifying assumptions, it gets shorter and have this simple relationship, sigma squared x transpose x inverse. I'll show you next time how to match that. Yeah, I'll show you that next time. Okay, so we're learning more and more about regression. We still need to figure out how to estimate the sigma squared term. I'll show you that. And then we're going to learn approaches to doing actual inference, or tests. Here's a Wald test, like I mentioned, estimate minus null value divided by SD of estimate. There's also a more general technique called a likelihood ratio test, and one more called an F test. So we'll see all of those. Once you know how to do t-tests and likelihood ratio tests and F-tests with regression models, you can do a whole lot. Okay, we are out of time. Any questions? Okay, have a good weekend. See you Monday.